Okay, in this lecture, we're going to cover our section 6.4 material on the Gram-Schmidt process. So what is the Gram-Schmidt process? Well, it is a relatively simple algorithm for producing an orthogonal or orthonormal basis for any non-zero subspace of Rn. So we saw in our previous section, 6.3, that if we have an orthogonal or an orthonormal basis for some subspace of Rn, then that basis is particularly useful because we can express any vector within that subspace as a linear combination of the orthogonal basis vectors, and the weights for that linear combination are pretty easy to calculate given the vector that we're trying to represent and our orthogonal basis vectors. So if we have a space which has a basis that may not be orthogonal or orthonormal, we'd like to try to construct an orthogonal basis so that we can use the results from our previous sections. So we'll see how this will work throughout this section. So as our first example, which will illustrate how this method works, we will consider the following vectors, x1 and x2, which are two vectors in R3. They're clearly linearly independent since they're not scalar multiples of one another. So they span some plane in space. And we're going to let W refer to that plane, the span of this set of two vectors. And our goal is to construct an orthogonal basis of vectors v1 and v2 for this space W. So to do this, let's start by defining the orthogonal projection of x2 onto the vector x1, which I'm going to denote as P. So we're going to let P be the projection of x2 onto x1, which we know is given by the dot product of x2 with x1 divided by the dot product of x1 with itself times the vector x1. So if we look at the orthogonal projection of x2 onto x1, then the component of the vector x2, which is orthogonal to the vector x1, is given by x2 minus this orthogonal projection, P, which lies in the subspace W, since it is formed from the vector x2 and a multiple of the vector x1. So here the vector P, our projection of x2 onto x1, is some scalar times x1, and then the component of x2, which lies orthogonal to x1, which is this difference, x2 minus P, is then a linear combination of the vectors x2 and x1. So it must lie in W, since W is spanned by x1 and x2. So we're going to let the first vector, let's call it v1, in our orthogonal basis be the vector x1 itself, and we're going to take the second vector, which we want to be orthogonal to v1, which is x1, as the component of x2, which is orthogonal to x1. That is x2 minus P, so that is x2 minus the dot product of x2 with x1 over the dot product of x1 with itself times the vector x1. So here x2 was the vector -3, 14, -7. And then we are subtracting, let's see, the dot product of x1 and with x2, we have -9 minus 56 minus 35, altogether is -100, divided by the dot product of x1 with itself, which is 9 plus 16 plus 25, so 50. And then we're multiplying by x1, which was the vector 3, -4, 5. So out in front here, our scalar, where we're subtracting -100 over 50, that's addition by 2 times the vector x1. So let's see, we have 6 minus 3 would be 3, -8 plus 14 is 6, and then 10 minus 7 is 3. All right. So the vectors v1 and v2, where v2 was the component of x2 orthogonal to x1, is an orthogonal set, which we can verify by taking the dot product of v1, which was x1, with this new vector that we just produced, v2. So here we can double check quickly. If we take x1 and this new vector v2 and take their dot product, we have 9 minus 24 plus 15, which is indeed 0. So they are an orthogonal set of vectors. And they are clearly non-zero vectors. Which lie in W. So, since the dimension of the space W is equal to 2, since it was spanned by 2 linearly independent vectors, they form a basis for W. So the number of vectors in that basis, which is the dimension, is 2. That means that the set of vectors v1 and v2 is a basis for this space W, as guaranteed. So why is this true? By the basis theorem. Which was from section 4.5. So it said any linearly independent set of as many vectors as the dimension of our subspace would then be a basis for that subspace. So since we have 2 linearly independent vectors, v1 and v2, they're linearly independent because they are an orthogonal set of vectors, and the dimension of W is 2, that means that that set is a basis. So here we've constructed an orthogonal basis for our space W. So how do we know that these, or why exactly does this work, where we let v2 be the component of x2 orthogonal to x1? Well, let's consider the following. So x1 and x2 are vectors in space. So here, not drawn to scale or accurately or anything, but we have a representation of x1, some arrow in space. And then we have another vector, x2. And then we can take the projection of x2 onto x1 as this vector p. And so if we take x2 minus that projection, that gives us the component of x2 which lies orthogonal to x1. So this vector, which is x2 minus that projection, is orthogonal to x1 by construction. So those two vectors are orthogonal to each other, and they span the same space W as x1 and x2. So what we're doing is constructing two vectors, v1, which I let be equal to x1, and v2, which is x2 minus that projection. And by definition, that is orthogonal to v1. So we have an orthogonal set of two vectors. The dimension of our space is 2, so we've constructed a basis for that set where we have our basis vectors as an orthogonal set. So this is illustrating how we can construct an orthogonal basis for a subspace which is spanned by a given set of vectors. So let's look at a more general example. So this next example will more fully illustrate the Gram-Schmidt process. So here is our problem. We're supposed to construct an orthogonal basis for the column space of the following matrix. This matrix A, so the column space, recall, is the space spanned by these column vectors. So let's give these vectors names. Let's maybe call these x1, x2, and x3. So here, just for notational sake, I'm going to let W denote the column space of A, which by definition is the space spanned by the vectors x1, x2, and x3. Those are the columns of the matrix A. So as we did in our previous example, for one of the vectors in our orthogonal basis, let's choose one of those vectors, say v1, to just be one of our column vectors, maybe x1. And we're going to denote by w1 the spanning set of this vector x1. So it's some line in, well, line in quotations, a line in R4 here, since x1 is a 4-dimensional vector, which would be the same as the span of v1, since we let x1 and v1 be equal to one another. And then we're going to let v2 be the vector that is produced by subtracting the projection of x2 onto the subspace W1, which was the space spanned by x1, from x2. So that is, we're going to take v2 as, well, let me save a little room here. It's a relatively long problem. So here we'll say v2 is defined as the vector x2 minus the projection of x2 onto the subspace W1. Now W1 was spanned by the vector x1, which is equal to the vector v1. So that projection is defined as the dot product of x2 with the vector v1, which spans w1, divided by the dot product of v1 with itself times the vector v1. So let's see what we have here. x2 was the second column of our matrix, so that was 6, -8, -2, -4. Minus, let's see, we're taking the dot product of x2 with v1, which was equal to x1. So that is the dot product of our first two columns. So let's see what we have. -6, -24, -2, -4. So altogether, -36 divided by the dot product of v1, which is the same as x1, with itself. So we have 1 plus 9 plus 1 plus 1, so 12, times the vector v1, which was -1, 3, 1, 1. So here out in front, our scalar, where we're subtracting -36 over 12, that's the same as adding 3 times the vector v1. So we are left with 3, 1, 1, and -1. All right. So just like we had in our previous example, where we were letting v2 be the component of x2 orthogonal to the vector x1, we can say, in this case, as in that first example, v2 is the component of the vector x2 orthogonal to the vector x1, since x1 spanned w1. And the set of vectors v1, v2 is an orthogonal basis for the subspace, let's call it W2, which is the space spanned by the vectors x1 and x2. So we have a set of two orthogonal vectors, which form an orthogonal basis for the spanning set for the first two columns, but we have a third column. So to extend this, we'll use the same approach. So continuing from our work on the previous page, let's take the vector v3 to be the vector produced by subtracting the projection of the vector x3 onto the subspace W2 spanned by the first two columns of our matrix from x3. That is the component of x3 orthogonal to the subspace W2. So if we use the orthogonal basis v1, v2 of the subspace W to compute this projection onto W2, we have the following. So here, our projection of x3 onto the subspace W2, which is spanned by the vectors v1 and v2, we would take the dot product of x3 with v1 divided by the dot product of v1 with itself times v1, plus the dot product of x3 with v2 divided by the dot product of v2 with itself times the vector v2. So this same sort of linear combination for the projection that we saw in our last section. So let's see what we have here. For the dot product of x3 with v1, so those are the first and third columns of our matrix, we have 6 divided by the dot product of v1 with itself, which is again 12, times the vector v1, which was -1, 3, 1, 1, plus we had the dot product of x3, the third column of our matrix, with v2, which was the vector that we constructed on our last page. We have a dot product of 30, and then we divide by the dot product of v2 with itself, which is 12. Times the vector v2, which we constructed as 3, 1, 1, -1, So simplifying here, we're left with the vector 7, 4, 3, -2. So now, the vector v3 is defined by taking x3 minus this projection of x3 onto w2. So x3 was the vector 6, 3, 6, -3. That is the third column of our matrix. And then we are subtracting the projection that we just found, which was 7, 4, 3, -2. And that gives us the vector -1, -1, 3, and -1. So let us note that the vector v3 is in the space W, that is the column space of our matrix, because the vector x3 and the projection of x3 onto the subspace W are both in W. So here v3 was taken as x3, which is certainly in W, the column space, since it's one of the vectors within the columns of our matrix. And then we're subtracting the projection of x3 onto W2, which was by definition a linear combination of the vectors v1 and v2. So since we're taking a linear combination of our three vectors, we're guaranteed that we lie in the subspace spanned by those vectors. So since the dimension of W, that is the column space of our matrix A, is equal to 3, since it was spanned by 3 linearly independent column vectors, that means the set of vectors v1, v2, and v3 is a basis for W, since the set of vectors v1, v2, v3 is an orthogonal set of non-zero vectors in W. So here, since we have a orthogonal set of non-zero vectors in W, it's fairly straightforward to take the dot product of each of v1, v2, and v3 and show that those dot products are 0, so they do form an orthogonal set. So since we have an orthogonal set of non-zero vectors, that means that they are linearly independent. And if we have a set of 3 linearly independent vectors, which are spanning a space, a subspace W of dimension 3, that means that they must form a basis for that subspace, as guaranteed by the Basis Theorem from our earlier work section 4.5. So this set of vectors, v1, v2, v3, is an orthogonal basis for W. So the following theorem is a formalization of the couple of examples that we just looked at, called the Gram-Schmidt process. So here's what it says. If we are given a basis of vectors x1 through xp for some non-zero subspace W of Rn, we can define the vector v1 as x1, v2 as being x2 minus the projection of x2 onto v1. V3 will be the vector x3 minus the projection of x3 onto the subspace spanned by v1 and v2, and so on up through a vector vp, which would be xp minus the projection of xp onto the subspace spanned by the vectors v1 through vp minus 1. So this set of vectors v1 through vp is then an orthogonal basis for the subspace W. And additionally, the span of the set of vectors v1 through vk would be the same as the span of the set of vectors x1 through xk, where k is any value from 1 to p. All right. Now, so this Gram-Schmidt process is illustrating a way to construct a orthogonal basis for any non-zero subspace of Rn. And in some instances, we might be interested in finding an orthonormal basis. So recall that's an orthogonal basis of unit vectors. But we can think back to our earlier work from Chapter 6 and recall that an orthonormal basis can be easily constructed directly from an orthogonal basis. To do that, we would just normalize each vector within our spanning set or within our basis. So this Gram-Schmidt process allows us to then construct an orthonormal basis for any non-zero subspace of Rn. We start by constructing the orthogonal basis, and then we just normalize our vectors. So as an example of this, let's recall that in the first example we worked, we had constructed an orthogonal basis for a subspace W spanned by these two vectors, v1 and v2. And we were then supposed to find an orthonormal basis. So we just need to normalize these two vectors to accomplish that. So let's take the magnitude of v1, or its length, and then to normalize a vector, recall we just take the vector and divide each component by its length. So here the length of v1 is the square root of the sum of the squares of the components of this vector. So here 3 squared is 9, plus negative 4 squared is 16, plus 5 squared is 25. So we have the square root of 25 plus 25, or root 50. Now 50 is 2 times 25, and root 25 is 5. So this is the same as 5 root 2. And the length of the vector v2 would be the square root of the sum of the squares of our components. So 3 squared is 9, plus 6 squared is 36, plus 3 squared is 9. So altogether we have the square root of 54. 54 is 9 times 6, so we have 3 root 6 in simplified form. So to get our unit vectors for this basis, let's let u1 be the vector v1 dividing through by its magnitude, or its length, v1. So this would give us the vector, let's see, 3 divided by 5 root 2, negative 4 divided by 5 root 2, and then 5 divided by 5 root 2, which reduces to just 1 over root 2. And we're going to take the unit vector u2 to be v2 divided by its length, or scaling by 1 over its length. So here we would have 3 over 3 root 6, it's 1 over root 6. 6 over 3 root 6 is 2 over root 6, and 1 over root 6. So the set of vectors u1 and u2 is an orthonormal basis for the space W, which is spanned by the vectors v1 and v2. So that same space that we were considering in our first example. Now, the last part of this section is going to be on a certain factorization of matrices. So this factorization that we're going to talk about is a Qr factorization. Now, there's different types of factorizations of matrices. We haven't considered these a lot during the summer course, but they have some nice applications. Basically, a factorization of a matrix is a way to decompose a matrix into the product of different matrices, which we can then use for different applications. So one application that we saw was in the diagonalization of matrices, where we could decompose a matrix into a product of three matrices, one of which was diagonal, and then use that to find higher powers of a matrix, say like a to the 100th power. So this Qr factorization is another factorization which will have some nice applications. So let's talk about this factorization, see exactly what we're doing. So suppose that we have a matrix A, which is an m by n matrix, and its columns are linearly independent vectors x1 through xn. So if we were to apply the Gram-Schmidt process with possibly normalizations to the vectors x1 through xn, which are the columns of x1 of our matrix A, then this would amount to factoring the matrix A, as we'll see in the next theorem. So in this theorem 6.12 from your textbook, which is called the Qr factorization, we'll see that if A is an m by n matrix with linearly independent columns, then A can be factored as a product of two matrices, Q times R, where Q is an m by n matrix, so it has the same dimensions as A, whose columns form an orthonormal basis for the column space of A, and R is a square upper triangular invertible matrix which has positive entries on its diagonal. And this Qr factorization can have some nice applications. So to illustrate this, let's consider the following problem. We're asked to find a Qr factorization for the following matrix A, and notice that this matrix is the exact same matrix that we were considering in our previous example, this 4 by 3 matrix whose columns are linearly independent. So we found in our previous example that an orthogonal basis for the column space of A, which is the space spanned by the vectors that we found, v1, v2, x1, x2, and x3, is what we were calling our columns. So we had found an orthogonal basis to be this set of vectors v1, which we found to be -1, 3, 1, 1. v2, which was the vector 3, 1, 1, -1. And v3, which was -1, -1, 3, -1. So if we are normalizing these vectors, so here if we're trying to construct our Qr decomposition, we're going to let Q be the m by n matrix of columns, which are an orthonormal basis for our column space. So we have a basis for the column space, which is orthogonal as these vectors v1, v2, v3. Now to get an orthonormal basis, we just have to normalize these. as we did in our last example. So here, normalizing these vectors, we have a vector u1, which would be found by taking v1, dividing through by its magnitude. Now let's see. The magnitude of this vector would be, let's see, dot product of v1 with itself is 1, 9, 1, and 1, so 12. So our magnitude is root 12, or the length of our vector. So u1 would be negative 1 divided by the length, root 12, 3 over root 12, 1 over root 12, and 1 over root 12. U2 would be the vector v2 dividing through by its length, which is also root 12. So we would have 3 over root 12, 1 over root 12, 1 over root 12, and negative 1 over root 12. And then u3 would be the vector v3 dividing by its length, which is also root 12. So we would have negative 1 over root 12, negative 1 over root 12, 3 over root 12, and negative 1 over root 12. So our theorem 6.12 says that for this factorization, we could take Q to be the matrix which has these orthonormal basis vectors as its columns. So here we're going to let Q equal the matrix with column vectors u1, u2, and u3. So that is Q is the matrix where our first column is negative 1 over root 12, 3 over root 12, 1 over root 12, and 1 over root 12. Second column is 3 over root 12, 1 over root 12, 1 over root 12, and negative 1 over root 12. Then our last column, u3, is negative 1 over root 12, negative 1 over root 12, 3 over root 12, and negative 1 over root 12. Or more simply, we can think about this as the scalar multiple 1 over root 12 by the matrix negative 1, 3, negative 1, 3, 1, negative 1, 1, 1, 3, and 1, negative 1, negative 1. Now, we just need to find our matrix R, such that Q times R is equal to A. So there's a number of ways we could do this, but a simple approach is to make use of the fact that this matrix Q has orthonormal columns as, or orthonormal vectors as its column vectors. So if we think back to our earlier work from chapter 6, we saw that these types of matrices had some special properties. So let's make use of the properties of such a matrix Q. So we know that A is going to equal Q times R. So to find R, let us observe that the matrix Q transpose times Q is equal to the identity matrix. So recall from, I believe it was section 6.1 or 6.2, that matrices which have these orthonormal vectors as their column vectors satisfy this property, that Q transpose times Q is equal to the identity, or in other words, Q transpose is equal to the inverse of Q. So here this is since the columns of the matrix Q are orthonormal. So if we are making use of this fact, we have Q transpose times A would be the same as Q transpose, and then A is given by Q times R. So by associativity of matrix multiplication, we have Q transpose times Q, then times R, but that's equal to the identity matrix times R, which is just R itself. So to find the matrix R, we can take the transpose of this matrix Q times the original matrix A. So here, recall that Q was given by 1 over root 12 times the following matrix. So the transpose is then 1 over root 12 times the transpose of the matrix that we were just considering. So our first column becomes the first row, -1, 3, 1, 1. The second column is now the second row, 3, 1, 1, -1. And the third column is our third row, -1, -1, 3, -1, times the matrix A, which was -1, 6, 6, 3, -8, 3, and 1, -2, 6, 1, -4, -3. So the product of these two matrices, which are 3 by 4 and 4 by 3, is going to be a 3 by 3 matrix. And if we multiply this out, let's see what we get. We have root 12, -3 times root 12, root 12 divided by 2, 0, root 12, 30 divided by root 12, and our last row is 0, 0, root 12. So again, R by construction is an upper triangular square matrix whose diagonal entries are positive.